Let's start. Okay. Welcome everyone to a new session of the TVS Colloquia series. Today we have the great pleasure to have with us Luca Izzo. He's a staff researcher at the Naples Observatory and an associated researcher at the DARC at Niels Bohr Institute. And today he will tell us all about classical nova. So please, Luca, take it away.
Thank you, Priscilla. Actually, the pleasure and the honor is mine. So good afternoon, good morning, good evening to everyone, wherever you are located in this globe. So as I said, it's a pleasure to discuss with you about the role that the Vera Rubin Observatory will have on the study and characterization of classical novae, in particular in the very nearby universe. So novae, classical novae are the most faint explosions in the realm of astrophysical transient, but as I will try to convince you in this talk, are not the least interesting. So just a short introduction about novae. Let's start with some short historical introduction. So the first term, novae, was published about 2,000 years ago in the natural history book by Pliny the Elder in 73 Anno Domini. So, and in this book, Pliny was indicating the appearance of a new star as discovered by Hipparchus, the famous Greek astronomer, that was indeed appearing in the sky. Actually, at the epoch, these appearances were considered just as a sublunar event because of the current cosmology accepted at the epoch. Interestingly, Pliny the Elder, unfortunately, died during the eruption of the Vesuvius 6 years after the publication of the natural history. And just as nice consideration, the Vesuvius is a few kilometers from where I'm talking about. So let's hope that no eruption or pyroclast eruption will be happening in the next minutes. Just a joke. And actually, novae is a Latin word, and since Latin was the main language used for scientific and not only scientific publication until the 18th century, if I remember correctly, the classification of a supernovae were not well distinguished. In particular, the famous astronomer Kepler, he published a book which can be considered one of the first papers on a supernova explosion, describing the appearance of a new star, the stellar nova, in the constellation of Ophiuchus. And the famous supernova that was observed in the 17th century. Interestingly, just a note, this is a picture taken from his book. At the epoch, the position of stars, any star, was in general referred as the location where the figure of the constellation was reported in astronomical charts. In this case, the new star was located very close to the feet of the Ophiuchus constellation. This is the translation of the title of this nice paper. And actually, with the improvement of technology, classical novae were discovered, of course, in our galaxy, but in particular at the beginning of last century, the people started to detect novae also in nearby galaxies, in particular in the Andromeda galaxy. And actually, novae provide also an important support for the famous great debate about the nature of spiral nebulae. And this was in particular related with the appearance of the famous supernova in M31, the supernova 1885A, where the discussion between Shapley and Curtis was related to the nature of this event, which was not a nova because it was at least a magnitude brighter than all novae known at the epoch. Interestingly, only 10 years later, people started to separate novae from supernova, and this happened with the paper by Lundmark and famous paper by Bade and Zwicky. So what are classical novae? Novae are thermonuclear explosions happening on the surface of white dwarf star that accretes matter from a late time and sequence star companion or in some cases also red giant, despite in this last case we talk about symbiotic novae. And as the matter piles up on the white dwarf surfaces, the temperature at the bottom layer or at the base of the accreted layer start to increase until it reaches the degeneracy value that leads to the ignition of thermonuclear reaction. Here, the production of a stable isotope allows the expansion of the external layer. And in this nice video, hello? Oh, okay. In this nice video that has been released by NASA, corresponding to the together with the very nice paper by Elias Eidi in 2020, there is a nice representation of how classical nova explosion happened. And this, in particular, with the recent observation, thanks to high-resolution spectrograph, and in particular the late-time imaging of nova remnant, actually the resulting explosion from the classical novae years after their initial outburst by the HSC and other optical telescope, and also compared by radio observation by radio interferometer that were shaping. Actually, they were they were imaging, the remnant from nova explosion. A new scenario for the explosion of classical novae was proposed that consists of multiple episodes ejecta that consist of an initial envelope of very thick, very dense envelope, mostly arranged along the equatorial plane with a lower velocity lower ejecta velocity. But since the white dwarf was still active, still burning, it was also, there is a message in the chat probably, okay, wait. It can energize a faster wind that can flow out from the less dense regions of this equatorial ejecta. And during this fast wind outflow, there could be an interaction between, a sort of internal shock between these two components that could give rise to shock that we will discuss later on in this talk. So this is a typical template of a classical nova outburst taken from a famous paper by McLaughlin in 1960. Actually, this template can be scaled in amplitude and also in time, because there are no two novae that shows exactly the same light curve. So we can distinguish different phases in nova explosion. An initial fireball phase, which is very rapid, based on the speed class, so it can also last for a few hours, and it's very difficult to catch out with also with the optical observation. And this corresponds to the rapidly expanding photosphere, which is not yet detached from the ejecta itself. Then as time goes on, density starts to decrease, the pseudo-photosphere detached from the ejecta, and the emission is reprocessed at a longer wavelength, giving rise to what is called the principal diffuse enhanced phase. Actually, corresponds also to the brightest phase of the classical nova explosion. And with time, due to the relatively larger velocity of the ejecta, the density also decrease. The ejecta start to become optically thin, and we start to see different photospectral feature until we reach the nebular post-nova phase, where from a spectral point of view, the direct product from the nova explosion can be observed as an emission line. This is an example of few light curve of some very recent classical novae that have been discovered in the recent year. On the left plot is an example of a very fast nova. It's one of the fastest nova ever known, with a T2 time. T2 is the time that the nova decrease of 2 magnitude in the V band from its peak brightness. And we can see also that nova displays a quite strong color evolution, based indeed on the different evolution of the nova ejecta. Other two novae are much longer events, And in particular, for the case of V5668 Sagittarius, we can also witness the presence of a dip in the light curve, which is more enhanced at the blue wavelength. This is due to the presence of dust formation in novae. Indeed, novae are also very well known as dust producers. So some theoretical consideration. Actually, the thermonuclear explosion, like type 1a supernovae, does not destroy the underlying white dwarf. This means that all novae are recurrent events. And recurrent times actually depends on the properties of the underlying white dwarf. Actually, it is strictly related with the mass of the white dwarf. So as for massive white dwarf, we have that the radius also is a bit lower, and we expect to have lower recurrence time for massive white dwarf. Indeed, in this table, it is shown typical that was published in famous paper by Truman and Levin in 1986. It is reported the expected recurrence time for different white dwarf masses. This also implies that we expect an inverse relation between the underlying white dwarf mass and the ejected mass, because for massive white dwarf, the surface gravity is much higher. So in order to reach the generative pressure and then lead to thermonuclear explosion, the white dwarf needs lower accreted matter on its surface to ignite thermonuclear reaction. And then, assuming for energy conservation consideration, higher white dwarfs are also connected with faster events because the lighter ejecta also reach optically thin condition much sooner than more massive ejecta events. And this also, these two plots show indeed a correlation between the ejected envelope for novae as a function of the T2 parameter. You see that for lower T2 parameter, the ejected mass is lower, as well as for the amplitude. The amplitude is the difference in magnitude from the quiescent state to the peak brightness of novae. We have that faster novae that are parameterized here by the logarithm of the velocity, of the inverse of the ejecta velocity, are indeed that for fast novae we have larger amplitude values. And this consideration also led already in the 90s to the proposal of a natural proposal of a correlation between the absolute magnitude at the peak in classical novae, relation between this absolute magnitude peak with respect to the T2 parameter. And in the literature, in particular, there is a review by the Lavalley and Mozzi where they present several formulations of this correlation, which is the maximum magnitude and rate of decay. There are several analytical representations. Actually, the most used one is a sort of S-shaped like correlation, which is widely represented in the famous plot where all the astrophysical transients are reported. Interestingly, the MMRD has also been used as a possible distance indicator for classical novae, despite the uncertainty on the distance is not very tight, of the order of 10%, the distance provided by the MMRD. And in this plot, it is reported the comparison of distances obtained using the MMRD versus distance obtained by the Gaia satellite. You can see that there is almost very good relation, one-one correlation. Another interesting observational evidence that is also supported by theoretical consideration is that, in general, fast novae, then events associated with massive primary white dwarfs, are mainly observed at lower galactic latitude. So in the disk, I'm talking about now at the moment on galactic novae. So here in this plot. This means that fast novae are mainly observed along the galactic plane, where we have the worst forming regions and younger and low metallicity stellar population, while slow novae that are associated to lighter white dwarfs are observed mainly at higher galactic latitude. And this is a component that is also in general called the bulge component. This this evidence points out to the existence of different nova stellar population, and this evidence has also been observed sorry, in some very nearby galaxy. In this plot, in the left plot, it is shown the distribution of classical novae as a function. This is the cumulative distribution, classical novae as a function of the rate of decay for the Milky Way and the M31, sort of Milky Way-like galaxy. You can see that the distribution for these two galaxies is very similar, while for the LMC that we know is a smaller galaxy, blue galaxy, star forming, low metallicity, we have a higher concentration of fast novae compared to slow one. And this is also supported, as mentioned before, by theoretical studies, by stellar population study of white dwarf forming stars. In particular, several study points out that the more massive white dwarf, the order of 1.2, 1.3 solar masses, primary, that are the progenitor of fast novae that are located in star-forming region, originated from the regiment sequence star of the order of from 6 to 7, maximum 8 solar masses. This points out to the fact that there is a sort of fast prompt channel for nova-like producers that come from the more recently formed stars that are more the more massive among the classical nova progenitor systems. And I also want to mention another paper recently published by Kemp, where they demonstrate still using some advanced stellar probability that takes into account star formation and metallicity, that low metallicity in particular implies shorter lifetimes, more radii, and larger remnant masses for the white dwarf that are produced in low metallicity region. And this has direct effects on nova rate, and in particular nova population. Indeed, in this bottom right panel, you can see that in the thin disk region, we expect a larger concentration of massive white dwarf. And this automatically points out to another topic related with classical novae, which is the possibility that classical novae can be a progenitor for type 1a supernovae. We know that there exist two main scenarios for the formation of type 1a supernova, which is the single-degenerate, which is actually exactly the binary system but the binary system producing classical novae, where we have a white dwarf that is accreting mass from a companion star, or otherwise we have the double degenerate scenario, where type 1a supernova can form from the merger of two, not CD, sorry, it's white dwarf in a closed binary system. And also recently Starfield and colleagues have also demonstrated that in principle fast novae can be an important channel for the single degenerate for type 1a supernovae in the context of the prompt channel. Actually, there are observational evidence since that they are based on the study of recurrent novae, fast novae, that suggest that the role of novae as possible type 1a supernova progenitors is not very important. So only a fraction of 10, maximum 20% of all type 1a supernovae can be formed from classical nova-like systems. And this some other consideration and recent results that are related with classical nova is that during the thermonuclear runaway, the thermonuclear explosion giving rise to classical nova outburst, we can have the formation of an isotope of the beryllium, 7 beryllium, that can be produced to this nuclear reaction where we have a helium atom that reacts with an isotope of helium, the trillium, giving rise to this beryllium isotope. And the only decay channel for the 7 beryllium is through electron capture that give with an half-lifetime decay of about 53 days, producing 7 lithium. And in recent years, I've been working a lot on the possibility to investigate the role of classical novae as a main factor of lithium in the Milky Way, and there are several papers about this result. An idea that has been proposed already in the 70s by Starfield et al. Through the Cameron-Fowler process, also Arnold and Norgard. And actually, this plot summarizes our current search for the beryllium line and the estimate of the abundance of lithium in classical novae. From an observational point of view, we have that the lithium yield inferred from the analysis of optical spectra is about 1 order of magnitude higher, larger than theoretical expectation. In particular, very recently, we have also studied 2 novae in the Small Magellanic Cloud, discovered by the assassin Salvidi. Here is the light curve from these 2 novae, and from the lithium yield inferred from this 2 novae, which is at the border of the theoretical region and the observational one, we have demonstrated that we can explain the observed abundance of lithium despite the chemical evolution code will start from the speed plateau or from the CMB abundance value. Maybe we can discuss another occasion this particular topic, but just want to underline that the study of novae in external galaxy is, in particular, the characterization of the nova rate will be important also for chemical abundance investigation. Another very recent result is that classical novae have also been detected at very high energy in gamma rays. And unlike symbiotic novae, where the interaction is between the nova ejecta with the winds surrounding the white dwarf, producing the nova explosion, for classical novae, the idea at the base of the high energy emission is related with the interaction that I have mentioned in one of the previous slides, interaction between the fast wind with these lower equatorial ejecta. So here, in the left panel, it is shown, bottom panel of the left plot, it is showing the optical light curve of V1369 Centauri. You can see the optical light curve is mainly composed of several rebrightening after the first initial rise phase. We have the detection in gamma rays happen only a few days after the initial discovery of nova, corresponding to the first rebrightening in the optical light curve. And this is explained as the shock between the 2 components that give rise to particle acceleration emitting them gamma rays. But interestingly, we also have observed with quite good temporal cadence the evolution of this nova, and corresponding to the first rebrightening at this position, we have the appearance of an additional ejecta component at a larger velocity, as clearly identified in the P Cygni line of the sodium, of the neutral sodium transition. This also has been the evolution of velocity due to this interaction has also been found in narrow iron peak elements, narrow metal lines in another nova in V906 carried by Elias Heidi, suggesting that indeed the shocks could have an important contribution in shaping the optical light curve of classical novae. So now let's go to the core of this talk. Why it's important to study the nova rate in nearby galaxy. I hope I have provided enough information to answer to this question. In particular, the knowledge of the nova rate is an important ingredient for the estimate or role of novae as chemical element factor, in particular lithium, but not only lithium. Novae are also producers of isotope as well as of dust, not only isotope, also aluminum and sodium isotopes, and also dust producers. And the nova rate is an important ingredient to quantify the amount of total yield of for each element from classical nova. The nova rate is also important, particularly the fast nova rate and recurrent nova rate is important for quantify the contribution of novae to the single-degenerate channel for type 1a supernovae, and the characterization of different speed classes in classical novae compared to their distribution in each external galaxy would really help to study the different stellar population producing classical novae and not only the event, and also other important primary topics like dust production, emission gamma rays, and also neutrino, because hadronic interaction happening in symbiotic novae as well in this internal shower of classical novae could produce possibly neutrino emission. All right, so in recent, well, not recent, the literature in the last 20, 30 years, the nova rate was already, the estimate of the nova rate in several galaxies, according to their color, was provided by several authors. And the main evidence, the main result was, the first result was that for different color of their host galaxy, we have a larger specific nova rate, so event per year per unit luminosity of the host galaxy, which is higher for bluer than young star formation host galaxy. In particular, red galaxy displays specific rate that seems to be 3-4 times lower than star-forming galaxy. These plots resemble the results obtained for not only for class but for type 1a supernovae obtained by Manucci et al. In 2005, where the rate of type 1a supernovae is higher for blue galaxy. But very recently, on a survey in M87, which is a massive elliptical galaxy, early type galaxy, in the Virgo cluster, made by Mike Shara using a lot of time with HST, it found an enhanced nova rate, in particular along the jet of M87. And this image, the left image shows the distribution of novae reported by Mike Shara. Actually, you can see a sort of enhancement, an increase of density of novae found by Shara himself along the jet of M87. This is a very nice result, but more interesting was the total rate of novae that he found in M87 from his survey, a very large rate, more than 300 novae per year. Which did give rise to this, higher specific nova rate for this particular galaxy. So this is still an open topic, and we need more complete survey to understand and to characterize much better this specific nova rate. Just want to mention another important result obtained by the Ogle survey, sorry if my pronunciation is wrong, where they have observed the two Magellanic Clouds for several years, and they have provided a very accurate nova rate events in these two nearby galaxy satellites of the Milky Way. You can see that they also provide very nice light curve that resemble a typical nova. All right, so let's go finally, let's move now finally to the role that Vera Rubin Observatory could have with classical nova. So we know, and I hope to be updated on this number, that for a single exposure in a normal operating survey by the Vera Rubin Observatory, we can reach very deep magnitude limits of 24 magnitude in the R band for a single visit. And since we will have a good temporal cadence for different filters, take into account that, all right, if I'm not wrong, the most updated value for the visit of the same field using the same filter in particular for the R band, is visit each 7 days. But in principle, we novae emitting on all wavelengths, we can have a good coverage, also using observation in other filters, and this can provide almost accurate value, not only for the peak magnitude of novae, but also for the time decay. And using the value of 24 magnitude as 5 sigma point source depth for a single visit, we could characterize nova rate for different speed classes novae, from the very fast ones, which peaks at -9 magnitude, to the most slow novae that peaks at about -6 magnitude. You can have a good characterization, a complete characterization for all galaxy in a volume with a radius of 7 megaparsec. And in principle, within this value, we expect as a first computation a daily rate of about 100 novae as detected by LSST. This is a picture that I found on the web that provides almost the entire map. I'm sorry if galaxies are very tiny in this image, but provide the almost a complete characterization of the local universe up to 8 mega years. Of course, we have a concentration surrounding the Milky Way between 1 megaparsec, and of course, well, the group associated with M31 Andromeda, which is not considered for LSST study because it's in the northern hemisphere. But already for the very close universe, there are a lot of galaxies, mainly small, faint, irregular ones, but there are also some nice, more extended galaxies that can be easily studied and characterized by the Vera Rubin Observatory. Just want to show a couple of examples. Let's take the case of Stexans B, faint irregular galaxy at a distance of 1.4 megaparsec, which corresponds to a distance modulus of 25.7 magnitude. So according to the specific nova rate, based on the luminosity, on the color of this galaxy, we expect a very low nova rate, about the order of 1-2 events per year. Considering this absolute magnitude, in principle, we could detect it transient up to absolute magnitude of -2, considering also the threshold of a single visit from LSST. While for the case of the spiral star forming NGC 5068, which is a 6 megaparsec distance, a distance model of 29, same consideration, we expect an nova rate similar to our Milky Way of 30-40 events per year, maybe more, maybe less. But we can, with a single visit of LSST, have a complete coverage up to -5 magnitude in terms of absolute magnitude. These numbers do not consider at all extinction from the internal galaxy. For the extinction, we will arrive soon. Just want to say that for this colloquium, I was working on a notebook trying to simulate LSST data, in particular the expected nova observation with LSST, but I did not have the time to complete my notebook, also because in the last 2 months I was very swamped by other duties. Just want to mention the Seeing project, a project that I'm leading and I've started this year, in February this year, using the VLT survey telescope. It's a program dedicated to observe a sample of about 25 host galaxy in the very nearby universe at distance lower than 5-6 megaparsec. And the main goal is needed to characterize the nova rate for different galaxy type, as well as to characterize the nova population according to the speed class of nova. There are also some byproducts that can be obtained not only by this project, also by LSST, which will be the possibility to discover some slightly more luminous trend like ELOT, and possibly to detect failed supernovae, but not talking about this. Here just some snapshot of some of the data that we are obtaining with VST. Please, we can observe different type of galaxy like NGC 3521, the very nice spiral ones, or the famous Centaurus A, as well as the galaxy that is there or not is there, like the Carina dwarf spheroidal galaxy, which seems there is nothing here, but there is a very faint dwarf irregular galaxy. And here an example of the procedure that we are employing here, just using different image analysis to detect transient typical analysis. This is an example on sextans B. And what I would like to show as very nice test that LSST can also that I was planning to do with LSS data is to simulate an RS Ophiuchi-like explosion. RS Ophiuchi is a recurrent nova, symbiotic nova, one of the possible supernova type 1A progenitors proposed by several people in the literature, characterized by a T2 value of 7 days. So we have simulated an RS Ophiuchi-like event in NGC 3109, a galaxy that is 1.2 megaparsec far from Milky Way with a distance modulo of 25.5 magnitude. Assuming a R-band absolute magnitude at peak of -8 and an extinction in R-band of 1 magnitude, this is what we expect to observe with VST. So in the left panel, our template image, in right panel, our source injection simulation, assuming a two-dimensional Gaussian with additional of some Poissonian noise. This is the expected emission for 18.5 magnitude at the peak of the nova, here at T2, and then as the nova fades up to the threshold level of 23 magnitude for the case of VST. So take into account that LSST can go deeper, at least or 1 magnitude deeper than the VST, so we can definitely detect a lot of these events in nearby galaxies. So this was my last slide. I'm perfectly in time, so we can have a lot of time for discussion. Just want to again mention that Vera Rubin Observatory will have a very important role. It's a very will be a very nice classical nova machine, particularly classical nova in nearby galaxy, and we expect to observe dozen, if not 100 of nova per day in the entire local universe. The nova rates, as I have tried to convince you, is an important parameter for the study, not only of the role of that nova could have as a chemical factory, factory of different elements in nearby galaxy, but also as indicator, as a proxy for the stellar population in all these galaxies, and also to understand the role that nova could have as a possible type 1A supernova progenitor in the single-degenerate channel. The cadence, and also the duration of the cycle, which is another important parameter, which at the moment is about 10 years, will definitely provide the most complete survey for these events in the nearby universe. Will be much better than any other survey done for these same purposes. And of course, there are several byproducts that could be obtained by this study, like, for example, the possible detection of failed supernova events, but also many studies on stellar variability in these galaxies. So that's all. Thank you very much for the attention.
Thank you so much for the super interesting talk. And with this, I will stop the recording.